Okay, so welcome back. So now what we're going to do is, in this video, we're going to start talking about describing a spiral. So spirals were the common parametric, not parametric, but polar curves that we will study and that we will use that come up a lot in nature. For example, the Nautilus shell, right? So these types of figures come up in nature all the time. Spirals, the golden ratio. You can see this spiral, and in fact the golden ratio comes up in things like this spiral that you'll see in a shell. Okay, so in this particular one, we're saying it has a circular pattern. Okay, so it's going out and it's like a circular pattern, where the Nautilus, as you'll see, has more of an elongated type of swirl. But we're going to start with this one, and we're going to see, can we describe this curve using the Cartesian coordinate system? And the answer is yes, we can describe it using x and y coordinates. So let's do that. Let's see if we can derive that. So let's assume, for the sake of this one, that it's starting here and it's going out from the center, from the origin here, at a constant, not a constant rate, but it is, let's say that the distance, right? So the distance OP, so the distance from the origin to the point, so this distance is changing as a constant multiple of the angle that it creates with the positive x-axis. So let's say we have, again, so we've got the positive x-axis here, got the y-axis here, and so with the positive y-axis here, we're saying we're going to call this angle, right, theta. So we're going to say that the distance OP, the line segment OP, changes its length, so its length increases as a constant multiple of the angle theta, okay, that the line segment creates with the positive y-axis, okay? So as it's going counterclockwise around, it's increasing, and the amount of the increase is a constant, based on a constant multiple of the angle theta, okay? So that's what we're doing. So then we're saying the distance, in other words, let's put this here. So the distance OP, right? The distance OP is then equal to K times theta. That's basically what we're saying, where K is some constant, okay? So as theta increases, the distance is also increasing, okay? So that should make sense. That's the idea. Okay, now let's use the distance formula, and let's use some trigonometry to change this into something in terms of x and y. Okay, so let's start with this side. Well, again, we're going from the origin, right? So this is centered at the origin. So the distance from P to 0 is given by the distance formula. And so the distance formula is given by x minus 0 squared plus y minus 0 quantity squared. Okay? Okay, that's one side. And the other side, let me do some, so what's theta? Okay, we gotta remember, we gotta bring in x and y. So we gotta get rid of theta. So the only thing that we know from theta that we can use is tangent theta equals y over x, okay? So that means, what is theta then? Well, then that would mean theta is equal to tangent inverse of y over x, or arctangent, the arctangent of y over x. So So now we can rewrite this as k times tangent inverse of y over x. Okay, so now we got everything in terms of x and y now. Okay, so now let's simplify this. So we get the square root of x squared plus y squared equals k times the inverse tangent of y over x. Okay, so now, what do we do with this? Well, this is, let's see, how are we going to do this? Well, we've got the square root of x squared plus y squared, okay? And k times the arctangent of y over x, okay? So, let's just solve this for the inverse tangent. So I'm just going to get this by itself, because if I can get this by itself, then I can take the tangent of both sides, right? Because I eventually need to get the xy out of the angle here. Okay, so let's do that. So let's divide both sides by k. Okay, so now we get the square root of x squared plus y squared over k is equal to tangent inverse of y over x. And so now I'm going to take the tangent of both sides. If I take the tangent of both sides, I get the tangent of the square root of x squared plus y squared over k equals y over x. And then now all I have to do is multiply both sides by x, and I get my final result. Okay, now the thing about this is this is all fine and dandy, but there's no way we can solve this for y. Okay, because we've got y here, but if we try to solve here, we'll end up with tangent or arctangent somewhere. So this is going to be very difficult to solve or write as a function of x. But if in polar coordinates, it's very easy. It's very simple. Okay. In fact, if we go back to this right here, this becomes very easy. Because if we go back to this part right here, if we go back to this, okay, or even further back, right? What's this side? Okay, so in fact, if we look at this right here, what is this? Well, x squared plus y squared is just r squared. So the square root of r squared is just r. So what do we end up getting? The familiar result that we talked about in the previous videos. We get r equals what? K times theta. Which then we can see what happens easily, right? As k increases, right, r is increasing, the radius. So it starts there. When theta is 0, r is 0. And then as theta increases, r increases, and we see the spiral. And again, positive in the counterclockwise direction. So in other words, we could actually have, if we wanted to do the entire spiral, we could set theta from positive infinity to negative infinity. And that would describe the entire spiral. Now, we can also add, let's see here. Now, one thing. So notice that it emanates from the pole, right? The origin. Okay. we could remove this restriction by adding another constant, adding or subtracting another constant to this. Okay, so we could have, for example, we could write this as R equals A plus K times theta, right? Okay, for our arbitrary constants A and K. Okay, so then we could move things around. So this would become a translation, right? So we can move things around. Okay? And now, this type of spiral is referred to as the Archimedean spiral, named after the Greek mathematician Archimedes. Okay? So this is referred to as the oops, hold on. Okay. And again, it was named after the Greek mathematician Archimedes, who was also an inventor, who invented the auger for transporting water. Okay, so anyway, so now in the next video I'm going to do another spiral, which is actually more related to the shell, the nautilus. Okay, so the spiral that we normally see when we take a cross section of a shell. Okay, and that's called the, it's more of an elongated spiral that more closely relates to the nautilus. So in the next video, I'm going to do the same thing, and we'll talk about what that shape looks like. Okay? And I'll see you then. Have a great day.